Okay, let's take a close look at the precise definition of a limit.
Okay, so we are dealing with the limit as x approaches a of f of x equals L. And the strict definition of this is that if we have our function here, there's our function f of x, and maybe we have a hole here, and so this is L, or the way this is defined, we say for every epsilon greater than 0. Okay, what is epsilon? It's a small positive number. For every epsilon greater than 0, and what that is referring to is we add a little bit to L and we subtract a little bit. When I say a little bit, I'm talking about epsilon. In other words, we can go a tiny amount down here, that would be L minus epsilon, and a tiny amount up there, L plus epsilon. And so we have this little yellow neighborhood here around L, that's epsilon above and epsilon below L. And the idea, we're saying for every epsilon, that means one person could say epsilon is 0.1, and another person could say it's 0.001, and another person can say 0.0001. And these little hash marks just keep getting closer and closer to L with never actually being on top of L. Okay? So that's the idea, and that's the concept of a limit, right? You can get your y value as close as you want to that value L. And so I want you to imagine these two little hash marks, which actually I'll do them in red. These two little hash marks in red, imagine they can move closer and closer to L, but never be on top of L. And if I go straight across from those, right, straight across here, and then down, and straight across here, and then down, we end up with a little neighborhood on the x-axis, right, on the x-axis, which I'll do in green. And as epsilon gets smaller, right, meaning as the red little hash marks get closer to L, the yellow region gets smaller, and subsequently what happens to the green region?
Get smaller.
It also gets smaller, right? The green region is dependent on what epsilon is chosen. And so down here we have A, which is what we would get to get us to that hole. And so the idea is for every epsilon greater than 0, no matter how small we make that little yellow region, there exists delta, also greater than 0, such that, okay, now what is delta? Delta is also a little distance, but in this case, it's horizontal here on the x-axis, a little bit above A and a little bit below A. And so as you guys just said, as I pick a smaller epsilon, we end up with a smaller yellow region, which gives us a smaller green region. But for each epsilon, we can find an appropriate delta so that any point I pick in the green region is going to translate to a y value in the yellow region. Okay, and the way we write that statement such that if I pick a point x in the green region, okay, well, what does that mean? That means that, so that's greater than 0, such that, remember the distance between some value x, and I'm saying the purple is my x, right? So purple, this is our x. As long as we pick an x that is a distance from A that's less than delta but greater than 0. Okay, so again, remember we talked last time that this is the distance between x and A. As long as the distance between our purple point and A is less than delta, it puts us in the green region. So such that if this is true, then we're guaranteed that the distance between f of x and L is less than epsilon, meaning that the purple dot on the y-axis is in the yellow region. So this part here is saying as long as I pick an x in the green region, I'm guaranteed I get a f of x in the yellow region. That's what those are saying. Okay. I realize that this is tricky stuff, but that's the idea. That's the definition. Okay. As long as we pick a purple x, right, in the green region, we're guaranteed to have a purple f of x, a y value in the yellow region. And we can do this for every single epsilon, which means that we can take these red guys here and get them closer and closer together. Okay. Now, that being said, if we look at example 2, what they're saying here is they're telling us the limit right here in blue, and they want us to find delta, which is that little distance along the x-axis above and below A, such that we have this right here. This is our epsilon 0.01 whenever x is within a distance of delta from 5. So that would be this part here. Okay. And to do this, what we're going to do is we're going to notice that we want this to be true, right? We want this. And if I manipulate this a little bit, I think I get something like this. And I can factor out a 2 out of the absolute value signs. And I can divide, so I get 0.005. So what I've done so far is what I call analysis. We've analyzed what's going on. And we've done a bunch of algebra, so these statements where we started and where we ended are mathematically equivalent, right? So the bottom part says, as long as we pick x's that are within a distance of 0.005 of the number 5, right? This is the distance between x and 5 is less than 0.005, right? That's what that says. Then we're guaranteed that this will be true because we can do all of our algebra backwards. Okay? So, in other words, if we choose delta equal to 0.005, then 0 less than x minus 5 in absolute values less than 0.005 guarantees that the distance between the function, distance between f of x and L is going to be less than 0.01. Notice that f of x is the function here. That's f of x. And this is the limit L. So what that is is 2x minus 7 is f of x minus our L, which is 3, is less than 0.01. Okay? So what the statement in blue is basically saying, as long as we pick delta to be 0.005, looking at the analysis that we did, all that algebra, we see that that's equivalent to saying that the distance between, I'm going to do it in yellow because this was the yellow region, the little epsilon region that we saw on the y-axis. As long as we pick delta to be 0.005, then we're guaranteed that the yellow distance is going to be within 0.001 or 0.01. Okay? And you'll notice what's in yellow there is what we have in yellow up here, which is what's in yellow way the heck over here, which you can barely see because it's so small, right? That's the yellow region up there. And then the green region, which is what we have on the floor, that's what we have over here. Of course, I did it backwards in yesterday's example, right? This should have been yellow, and this should have been yellow. And then the green region is the region on the floor. All right. I'd like to do a question.
So basically, we took the first graph we did and then like applied the same concept to the example 2.
That's exactly right. Just a couple things that I'll point out. This yellow number here is epsilon. Okay. And so the idea, even though I didn't graph it, is our limit is 1, 2, 3, right? That's the limit L. You can see that in the original problem. And the epsilon is 0.01, which means that they're coming in here at 3.01 and 2.99, right? They're going way in there, and we're getting a tiny little yellow, whoops, that's not yellow, a tiny little yellow region right there, okay? And then, which is really hard to see, it's so small, right? But that's what they're doing, and then we have the graph of this function, which is 2x minus 7, right? That's going to be a line doing something like this. And they're saying as long as, let's see, and then from 3 here, we've got 5 down there, right? And so if we were to take that little red region and bring it straight across here and straight down, we're going to get a little region along here, right? And that little region there is going to be our green region. Samira, does that kind of make sense?
Yes, it makes sense seeing both graphs and everything. Thank you.
Good, good. And then real quick, the delta we found is 0.005, right? So we are 0.005 above, and we are 0.005 below, because delta is equal to 0.005. Okay, it's tricky stuff. Good questions. Yes, epsilon is always dealing with a little neighborhood around the limit, which is a y value, and delta is always for the x. That is correct, Hansel. Okay, so they want us to actually prove this thing. Now, when you prove a statement, an if-then statement, right? If you notice, we have this guy right here is an if-then statement. And so what we have to do is we have to state the if and show, right? We have to state this and we have to show that. Okay, that's how you prove an if-then statement. So what we're going to do is we're going to first find the appropriate delta. It says there exists a number delta greater than 0. So we're going to find that first, and then we'll write up the proof. And we're going to find it the same way we did the analysis on the previous problem. So just to be clear here, x is approaching a, which is 2. The function f of x is 3x minus 5. and the limit is L equals 1. Okay? And we're going to do our analysis first. And the analysis is basically saying we want, at the end of the day, at the end of our proof, what do we want? Well, we want the thing in yellow there at the end of our proof. That's what we want. We want to be able to show that. So we're going to reverse engineer it. We're going to start with f of x minus L less than epsilon and then use that to find delta. In other words, we want f of x minus L absolute value less than epsilon. While plugging in what we have there, f of x is 3x minus 5 minus the limit, which is 1, and we want that less than epsilon. Okay, I took that from the problem itself. And so this, of course, becomes 3x minus 6 less than epsilon. And then we factor out a 3, and we divide. And again, what we've done is this inequality here is equivalent to this inequality there, right? We just did algebra, but they are equivalent statements. And so what we're saying is whenever this is true, which says the distance between x and 2 is less than a third of epsilon, then this will also be true, which is the thing I want to show. And you'll notice that this is my green region on the floor, okay? Because what are we approaching? Our x's are approaching a equals 2, okay? So our choice for delta, so we choose delta equal to a third of epsilon, okay? And even though I don't need to do this picture to do this problem, I'm going to show you pictorially what this is. It's actually very similar to the others, of course, but let's go ahead and look at it real quick. So this time we have our limit at 1, so I'm just going to put a 1 there and a 2 there. Okay, and we've got 3x minus 5, so let's put a 1 here and a 2 there, just so it doesn't get too crazy. And we know that if we did direct substitution into this function, we would get 1, so our function actually goes through this point. And it's linear, right? It's got a y-intercept of -5, so it's doing something way the heck down there and way the heck up here. And pretend that's a straight line. I'm not going to take the time to make it perfect. Okay, so the limit is 1, which we saw from the problem. And the idea is if you pick a small epsilon, if you give me any epsilon, right? So again, a little distance above and a little distance below. That's 1 minus epsilon, 1 plus epsilon. That comes straight across and down here. And this one comes straight across. Pretend that looks right. And it comes down here. And what we just found is as that little region on the floor. So we already have something for our region up here, right? That's the distance between f of x and epsilon less than, I'm sorry, the distance between f of x and 1 is less than epsilon. That's going to give us a little region on the floor in blue. And what we just discovered is to make this work, we need that to be 2 plus epsilon over 3, and that to be 2 minus epsilon over 3. Okay, that's what we just did. We just noticed from the analysis portion that if we choose our delta to be epsilon over 3, then we can do all of this algebra backwards and we'll be inside the little yellow region. So if we choose delta to be this, then we're guaranteed by the backwards algebra above that this will be true. Okay, so that's the analysis portion of this. Now we have to actually do the proof. So the proof looks like this. And I'll tell you, the first time I learned this, basically my teacher had me memorize the outline of the proof, and I would just fill in blanks. So we always start with given epsilon greater than 0, meaning for any epsilon greater than 0, choose delta equal to blank. Okay, and I'll fill in the blanks in a minute. So if 0 is less than x minus blank, in this case it's 2, I'm just going to go ahead and write it, less than delta. Actually, you know what, here, let's do, I'll highlight all the blanks in a moment. Then we have f of x minus L, which is equal to 3x minus 5 minus 1 equals, okay, now before I continue with that, we've chosen delta to be epsilon over 3, okay? So notice what I've written for the if part. If the distance between our x value and 2 is less than delta, so we're delta close to the number 2, and if you look at that, that is this statement up here in green, right? That's that statement up there in green. That is the statement that basically says the distance between x and a is less than delta. So I have the if part, I have to show the yellow part. And so that's what we're doing. Here comes the beginning of the yellow part that I'm showing. I have to show that it's less than epsilon, right? I have to show that I'm in that yellow region on the y-axis. And so we do the math again. I know it feels a little bit redundant, but it ends up looking like this, okay? Now, I know that this green portion, right, this green absolute value, the distance between x and 2 is less than delta. But isn't green right there also? Yeah. So if I take a number and multiply it by 3, and I take 3 and multiply it by something less than that number, right? Right? This guy in green is less than this guy in green. And when I multiply each one by 3, I should have an inequality like that, right? From above in green, I know delta is bigger than the absolute value x minus 2. So if I multiply each one by 3, right, if I come up here and I multiply this by 3 and this by 3, I still have that less than sign there, okay? And that less than sign, which I'm going to do in red so it stands out, is the same as this less than sign here, okay? I just took both sides with the pink arrows and multiplied both sides by 3. And from there, I know delta is actually equal to, here in purple, epsilon over 3. So I get to write 3 times epsilon over 3, which leaves me with epsilon. Okay? And that what we just showed, I'm going to get rid of my green for the time being. Oops, got rid of my delta also. What we just showed, I'm going to highlight in blue because we haven't used blue, is that the distance between f and the function is less than epsilon. That's what I just showed, or we just showed. And if you come up here to the definition where I said show this, right? The distance between f of x and the limit is less than epsilon. That's what we just showed in blue down here. And so to finish it off, thus we have shown that if 0 is less than x minus 2 is less than delta, then 3x minus 5 minus 1 is less than epsilon. So by definition of the limit, we've proved that the limit as x approaches 2 of 3x minus 5 is equal to 1.
Professor?
Yes.
So for the part that we multiplied, or after we factored 3x minus 6, the reason why we put the 3 delta is because we need it to match the up on the top where it says x minus 2. And so because we have a 3x minus 2, we need to put a 3 in front so it matches the statement.
Right. So if you multiply both sides by 3, then we get that. Agreed?
Yes.
And so the thing to notice is it's all about this red inequality. I need that inequality. It's right here. This is the same red inequality. If you only read the stuff in blue, it looks like this, right?
Mm-hmm.
Well, almost. I should move this blue over to here. But it's the same thing. It's just, right? And so the thing we wanted to prove in blue is exactly the thing that we need to show up here in blue. Does that kind of make sense?
Yeah, so you take the green and blue and you just apply it to the problem that you're working on.
Exactly. Exactly. So the things that will change depending on your problem. So remember I said that my professor told us, hey, memorize this and then plug it in for each problem. So the things that will change are going to be this. I'm going to get rid of my blue for a moment. Oops, I lost 3 there. This obviously would all change. And then this would change. And of course, this would change because that's the problem. So everything in purple would get replaced depending on the problem. Okay, and of course your analysis would change, but you would follow the same steps. And if you notice, the examples I've given you so far, they're only linear. This example and the last one, the function is a line. The next one is also a line. I guess I also have one in my notes that is not in the print notes that is quadratic. It's a much more complicated situation. We're not going there in this class. You can do that in another class if you take that route.
Example 4, prove that the limit as x approaches -1 of -1/2 x plus 1 is equal to 3/2. So first let's make sure that we know what all the different parts are that we're dealing with here. So x is approaching -1, so that means -1 is a. This here is our function f of x. And this is our limit L, which is 3/2. Now, just as we did in the previous problem, we're going to start with the analysis. So we're going to let epsilon be greater than 0. And we want to find delta such that we get the conclusion of the definition, right? What we're trying to prove is that the distance between the function and the limit is less than epsilon. That's what we're trying to prove. So we're going to go ahead and manipulate this algebraically. Now we'll factor out the -1/2. And when the -1/2 comes out of the absolute value signs, it becomes positive. So we're going to put a +1/2 on the outside And I'm going to rewrite the x plus 1 as x minus negative 1. And the reason for that is because negative 1 is a, and so that's the distance between x and a, or x and negative 1. And that's less than epsilon. Multiplying both sides by 2. And so now we have the value that we're going to use for delta. So choose delta equal to 2 epsilon. And that's our analysis. So now we're going to go on to the proof. And just as above, we're going to write all the same words. We're just going to fill in the different information for this particular problem. So we start off with given epsilon greater than 0. Choose delta equal to 2 epsilon. So if 0 is less than the absolute value of x minus negative 1, less than delta, so remember that's the distance between x and negative 1 is less than delta. And sometimes people will write that this is equal to 2 epsilon. Then, so there's the if part of the definition of the limit. Now we have to show the then part of the definition, which basically says the distance between the function and the limit, which is 3 over 2. We need to show eventually that this is less than epsilon. And once we've done that, then we can write our conclusion and we're finished. So that's what we're going to work on now. And it's really just a matter of doing the same algebra that we did in the analysis, right? So we have negative 1/2 x minus 1/2. Factoring out the negative 1/2, it becomes a positive 1/2 on the outside of the absolute values. And again, I'm going to write x minus negative 1, so that's the distance between negative 1 and x. And now we're going to get the inequality with our delta, right? So these two inequalities are going to be the same inequalities. And the idea is that this quantity here, we know from above, is less than delta. So here you can see we've taken the part in green and we multiplied both sides by half to get this down here. So now delta is the same as 2 epsilon. The half and the 2 cancel and we're left with epsilon, which was the goal. And so what we've shown is that the distance between the function and the limit is less than epsilon, which is exactly the statement that we need from the definition of the limit. So we've done it. We're now ready to write our conclusion. So we write, thus we have shown that if 0 is less than the distance between x and negative 1 is less than delta, then the distance between the function and the limit is less than epsilon. Therefore, by the definition of limit, we've shown that the limit as x approaches negative 1 of negative 1/2 x plus 1 is equal to 3/2. And that's it. Now the notes go on to talk about one-sided limits. And it's basically the same definition. It's just you'll notice that we, with the left-hand limit, we are only approaching from one side, right? We have the delta only on one side of x, right? Or one side of a, if you will, I should say. And then the same thing for the right-handed limit, we are approaching from above, so we only get the delta added above. Now with infinite limits, I'll go ahead and graph a quick function so you can see what this is getting at. The basic idea is that we choose some value m on the y-axis, and we can always get a value on the function bigger than m by simply choosing x is close enough to a. So this part right here is saying that we're talking about a little distance around a little delta neighborhood around a. So as long as we pick x's within this little region here, and we kind of follow it upwards, we're guaranteed that any value in that little region down there, in that little delta region, f of that value will be larger than m. And we can do this for any positive delta. In other words, we can make the little region around a smaller, and it would just make m a little bit bigger. And as long as we pick an x value in here, f of that x value will be larger than m. Finally, down beneath that, we have a very similar definition, just involving a limit that's going towards negative infinity. And that's pretty much it for that section. Again, we're not going to be dealing a lot with epsilon deltas throughout the semester, but this is the underlying precision that you have with limits, and limits end up being the basis for integrals and derivatives, as we'll see in the chapters ahead.